Okay, welcome to our lecture as a fact, flexible AC transmission system and power quality. In the previous lecture, it was discussed the shunt compensation, the introduction of shunt compensation, and the best location of the shunt compensation, in which we have considered the location of shunt compensator or the ideal compensator at the center of transmission line. Means we have considered uh, two machine system. In two machine system, uh, acting one, both are connected together, simple two machine system, and ideal compensators were installed at the center of line. So by this one, we found that the without any compensation, the active power transferred by the two transmission line by two machine system is V square upon X into sine delta. This is our P delta curve is there. So it will give the maximum power. This is the angle delta. This power is P, and this is the maximum power, say P maximum. But if you install the ideal compensator at the center of the transmission line, it is found that the active power transmitted by compensated line is equal to twice V square upon X into sine delta by 2. It means that the maximum power is doubled, is the doubled value. So this is the, say we can say that the new, this angle will be the pi, and the power by compensated transmission line or midpoint compensation, this is the twice maximum, which we have considered in detail, twice P maximum. So this is the advantage of shunt compensation, which is connected to the uh, bed of the transmission line. Now, in today's lecture, our objective of lecture to understand the end line support with the and without compensation. Second point is that what is the causes of voltage instability and how it can be prevented. Okay, so today's our lecture's name is say it is the end of the line, end of line voltage support to prevent voltage instability. Voltage instability. So there may be a voltage instability. It is quite clear that the voltage instability, it is because of the deficit of reactive power, or it may be the surplus of reactive power. So for that purpose, we consider a radial system. In the radial system, say this is our generating station or the source. It is connected to the transmission line. The reactance of the transmission line is X, and at the end, load is connected. At the end, here, the load is connected. So it is not a two machine system. In two machine system, both sides, the two alternators are connected. And because in practice, there are large number of machines are connected, large area generating areas, large number of generating areas are connected to make the grid. But for understanding or our study is restricted to the two machine system. Now here it is a radial system. The impedance of load is say Z, and this is incoming bus and out receiving bus. The voltage at this bus is voltage VR, and the sending end voltage bus voltage is Vs. So this is simple. Radial machine is a radial system is there. So this diagram is a uncompensated diagram. Okay, here we have not connected any compensation, not in the mid compensation or shunt compensation at the receiving end. If you are considering this one, there may be a deficit of reactive power, there may be a surplus of reactive power, and because of the surplus and deficit of reactive power, the voltage profile, the voltage VR will not remain constant for all load condition. So under such condition, the characteristic of load voltage or the load voltage profile, it can be represented by the power. Here it is represented by the power in PU versus means voltage versus power. So here is a voltage is PU. So say this is the 1 PU, means 100% or rated voltage is there, and it is found that the variation of voltage is due to the change in power factor. Change in power factor means there is a change in reactive power. So it is we can plot the reactive power from 0.8. We can plot it from the 0.8 lagging, 0.8 power factor lag to the 0.9 power factor lead. Okay, so here the voltage is, say it is a 0.5. We can represent it as a 0.5 PU. It is a 1 PU, and it may be a 1.5 PU. Okay, this is a power in this one. So it is found that the voltage versus power curve for the low power factor, when the power factor is 0.8. So this is the instability at which the power does not goes to the more than 0.5 PU and there is a voltage collapse. Similarly, if we increase the power factor by 0.8, again the voltage is say it is up to the 0.8 PU. Say this curve is 0.8 power factor lag. This is 0.95 lag. This is the power factor, and say this is the unity power factor. This is the unity. So at unity power factor, if you maintain the power factor unity, definitely we come to nearly 1 PU power transmitted. So it is a unity power factor. And whereas if the power factor is increased in the leading side, the voltage may increase more than the 1 PU, and the voltage system instability is going to occur more than 1 PU of the power also. So it is say 0.97 power factor lead. So this is the leading side. So this is the voltage profile. This voltage profile says that the instability is going to occur. This nose of this one is going to occur the instability of voltage. Okay, so here the voltage is not constant. For the more lagging power factor, or there is a deficit of the reactive power, the voltage is decreasing. For the somewhat unity power factor, the voltage is somewhat constant. But as soon as the power factor goes to the leading side, there is a surplus of reactive power. And because of this surplus of reactive power, the voltage of bus voltage, receiving bus voltage is slightly greater, greater than the rated voltage. So this knows, or this is the points where it indicates that the voltage instability. The voltage instability can be avoided with the help of compensation, that is a shunt compensation. Now, instead of connecting the shunt compensation at the center of line, we are going to connect the shunt compensation at the receiving end. So this is uncompensated line, uncompensated line, and now we can represent it by the compensated line. Same, the reactance is there. At the receiving end, load is connected. This is the source. This is source voltage Vs as it is, reactance is X. Now here at the bus, this is your receiving bus, voltage is Vr as it is. Here we have connected ideal compensation or VAR compensation, static VAR compensation. So this is static VAR compensation. We are representing it. It is Z and it is say VAR compensator. Static VAR compensator is there. Now, when we are connecting the static VAR compensator, whatever the reactive power required, it may be a lagging or it may be a leading. Suppose it is a static VAR compensator consists of thyristor control, thyristor switched capacitor, then it is going to deliver the reactive power needed by the load, kVAR or MVAR, isn't it? Or if it is a under compensation, means the power factor of the load is more than it is a leading power factor, then it will be it is going to consume the lagging reactive power. So because of this VAR compensation, at the end of the transmission line or radial system to the load, the voltage profile can be, again we are going to draw the voltage in PU versus power in PU, and it is found at same 0.5 PU, 1 PU, 1.5 PU, and here is the 1 PU, 0.5 PU is there. So it is found that the characteristic under such condition is the voltage profile of the load is constant. So we can represent the constant voltage profile of the load. So here it is say 0.8 lag, it is unity power factor, and it is say 0.97 leading power factor. So it is quite clear that the uncompensated line and compensated line. In uncompensated line, the voltage profile is not constant, and whereas for the compensated line, the voltage profile of load is constant. And the VAR compensation, simply we can say that it is the APFC, automatic power factor controller, where the capacitor is going to switch either by say a thyristor control or thyristor switch. We are using thyristor switch capacitor. So we are going to increase the number of capacitors as the load is increases, and we can decrease with the help of VAR compensator manager. And in this way, we can maintain the voltage profile of the load is constant. So say if try to understand by this one. So here it is quite clear that the voltage end of line voltage support to prevent the instability. The objective of this lecture is to understand the load side compensation, voltage profile with and without static compensation, and causes of voltage instability and prevention of bias shunt compensation and transient stability. So transient stability we are going to conduct in the next lecture. But it is a simple, say, see, this is the radial line. It is represented, it is the sending end voltage. It is the load is connected at the second end with the transmission line, the reactance of the transmission line X. Here, the voltage versus power, the plot says that if the power factor is low, it means that there is a deficit of reactive power. There is a deficit of reactive power. Here, the deficit of reactive power is less, but whereas at the unity power factor, there is a no deficit or there is a no surplus of reactive power. The voltage is almost constant for a up to the 1% PU power delivery. But as soon as we increase the, if you go to the power factor more than, if you go to the power factor is leading, means there is a surplus of reactive power. The voltage profile, the voltage which may be the constant value is greater than the its rated value. So because of the surplus of reactive power, voltage get increases, isn't it? But we do not want, this is not our desired characteristic. Therefore, we have connected a shunt compensation at the load side. So this is the shunt compensation. This may be a thyristor switch reactor, isn't it? Or simply for our simplicity or for understanding purpose, because we can see the APFC, automatic power factor controller, where the power factor of the load remain near to the unity by setting the value in the reactive power manager. And there are a number of capacitors. For example, there is a 100 kVAR capacitor is bank is there. It can be divided into 20 kVAR, then 15, then 15. So it is 20, 60, then plus 10. So 70 plus 10, 80 plus 5, plus 2 plus 3. So if there are in these steps, so there we can obtain the smooth variation in the reactive power by connecting the combination of different capacitor. If the load is more, there may be a 15 plus 10, it may be a 25. If the load decreases, it becomes 15 plus say 5, 20 or only 120 kVAR. Or for the, so this is the core large change in the load is there, whereas 2 and 3 kVAR is used for the smooth variation in the power factor. So the shunt compensation, which is connected to the load side, the best example is the APFC. And if you are maintaining the APFC properly by a proper division of number of capacitor can be switched, and this capacitor switching is maybe by the say contactor, but it is going to control by the thyristor one. So if we can replace entirely the contactor by the thyristors, so it will give the static var compensator or this one. So here, what is the difference in the previous case? Here the voltage profile of load will remain constant at any power factor. So this is the advantage, and it will avoid the voltage instability in the system. So this is the event. Now in the next lecture, we will see the improvement of transient stability with the help of shunt compensation. So before going to the this one means transient stability, it is necessary to understand what to mean by transient stability and how it is going to judge with the help of some equal area criteria.